For the rest of the afternoon, we've got, right now we've got a joint session. So this will be a session with two PhD students. These are students that are jointly advised by David Parkish at Harvard and John Horton here at MIT Sloan. Afterwards, we'll have student flash talks. So this joint session, the talks will be a bit shorter, perhaps 20 to 25 minutes. I'll introduce Kehang in a moment. He'll have a Q&A that may be a bit shorter, so perhaps 5 minutes, maybe 10. So please be mindful of the time when it comes to the Q&A afterwards. So without further ado, I'll introduce Kehang. So Kehang is a fifth-year PhD student at Harvard. As I've mentioned, he's working with David Parkish at Harvard and John Horton here at MIT Sloan. Kehang is interested in studying AI agents as proxies for human decision-making, as well as how individuals collaborate with these agents in economic contexts. His research focuses on using LLM simulations to find novel patterns about human society and also trade-offs for deploying large language models as autonomous agents. Now I'd like to invite Kehang to give his talk.
Thanks, Adam, for the kind introduction. My topic today is automated social science, language models as scientists and subjects. This is a joint work with my collaborators in MIT Sloan, Benjamin Manning, and my advisor, John Horton. As an earlier speaker, Daniel mentioned in his talk, generating algorithmic recommendations or decision-making is always very hard. But in the new era of language models, maybe there's a new way to massively generate this. So this is one of the topic or one methodology I want to introduce to you today. First of all, a flash overview. This is a very high-level loop of doing scientific research. We start with generating hypotheses. Then, according to this, design experiments and run those experiments, whether in a lab, in the field, or running simulations. And then analyze the results, try to test the hypothesis or verify it. There is a lot of efforts in using language models nowadays in natural sciences. For example, in the mathematics, in chemical research, and novel material studies, they use language models to both acting as a hypothesis generator and then operating the machines, running experiments, analyze the results. The whole process can be accelerated. But in the field of social science or operation studies, how far can we push the automation of this scientific process? We already see there's many efforts in each one of the components. For example, in hypothesis generation, lots of papers propose machine learning or language models as a way to generate novel hypotheses. In terms of running experiments, there's a new methodology of using language model as a proxy for humans. For example, this is one digital version of me. I can prompt it to be, here's your name, your age, your city, education, and then I can ask this digital version of me a lot of questions that related with operational research or economics. For example, running a survey, play again, or answering a psychology survey. We can also make lots of these agents together, like a population or like a society, and have them talk with each other to simulate the real world. For this new methodology, there's actually a lot of papers seriously studying it. For example, there's Stanford paper building a whole society of these agents and finding there's emergent patterns as real human society. However, ever since the launch our work, there is some cautious voice about language model simulations can exhibit bias or even limited diversity. However, there's tons of other works show that language models can simulate human behaviors in certain scenarios, especially in economic studies. And many new methodologies have been proposed to build more realistic proxies. For example, fine-tuning or post-training More importantly, there's a very systematically reviewed paper by Stanford that shows that across many regions of psychology and social studies, language model simulations reach a very high degree with the real human subjects. So the caveat here for this talk is, well, let's suppose AI simulating human minds works in some sense, and we will move on to the next talk of analyzing the results. It turned out this task may be the easiest one because with the well-formulated experiment plan and hypothesis, this hypothesis testing goes along with that. We can use the R package to easily do the job. With all these components in hand, we want to ask the question of how far can we actually push the automation of this scientific process from hypothesis generation to running experiments to analyzing results and iterate the hypothesis along the way. And the second question is, does this kind of system produce credible findings? And of course, at the end of the day, we want to ask for external validity of can the system generate valid and even novel findings along the way. So for in case people are so anxious to know the answer, I will give this in front. Yes, we do build a system that automate the whole process. And yes, the system do generate some proof of concept findings. For the third one, it's still ongoing, and the answer is highly probably yes. So the plan for today is I will try to explain the system we have already built and share some results. I will go through some validation set and try to show you the efforts in pushing for finding something new in my future work. So just follow the sense of this loop of hypothesis generation, experiments, and data analysis. The system can actually do all of those in the following order: generating hypotheses, design experiments, and then, more importantly, generate agents as experimental subjects, and then run experiments with these independent language model subjects. Collect data, analyze the results, and iterate or test the hypothesis. Here's a high-level visualization for this computational system, and I will go with you one by one. So first of all, the first step is specifying the social science scenario. I want to know that this is the only scenario involves human input. So a user, basically me or any researcher, need to provide open-ended description for the social scenario. For example, two people bargaining over a mug, or like an auction, or any decision-making process. Then, based on this open-ended description of the scenario, the language model scientist will go on to generate a hypothesis as a structural data source. Here, we use DAG as the model. It will tell exactly how to design experiments and also exactly what kind of data analysis the language model scientists need to do after collecting data. All right, so here is the example of two people bargaining over a mug. So this is the sentence I sent in for the system. Then, based on this scenario, where I stated here as a variable, the language model scientist will ask what kind of potential outputs, outcomes that the social scientists may be interested in. It can be under this scenario, it's maybe a deal occur, or whether there's an agreement and what's the price for the agreement. This is like the underlying source code. Somehow they showed up. I hide them away, but somehow the system exposed itself. Anyway, as the next step, with this outcome, suppose the system selects deal occurrence as the outcome, then the next question generated by the language model scientist will be for this specific outcome in the scenario, which are the potential causes. This can be the buyer's budget or buyer's value, and the seller's, or maybe more exotic, like seller's sentimental attachment as an emotional factor. The key point is that the system will generate a bunch of candidates for these causes or outcomes, but human researchers can still intervene or replace some of the decisions we make. The system make. So after that, with this model built in the DAG, the system tried to operationalize these variables by assigning a type for each one of them, like the deal occurrence, a binary outcome. And because the buyer's budget and the seller's sentimental attachments are the causes, so the system will also go on to introduce a variation for each one of the variables. So for example, the buyer's budget will be assigned a bunch of variations from $5 to $40. And seller's sentimental attachment to be a categorical variable from indifferent to very attached to highly attached. With the models from step 2, the system go on to create agents with specific instructions and variations. For example, in this 2 people bargaining over a mug scenario, the system will typically build 2 kind of agents, one buyer agent, one seller agent. And they will be endowed with specific goals and constraints. Like for the seller, their goal is to sell the mug at the highest possible price. And also with one specific exogenously varied attributes. For example, one of the seller will be endowed as you are highly attached to the mug. With these agents, the system will then decide how does we researchers, as we researchers design experiments, the system will also determine how these agents will interact. So this includes how to send outputs and how to receive the inputs from other agents. So as a real bargaining scenario. Here is two example of a buyer with $10 budget interact with seller, and a buyer with $40 interact with the buyer. The system will launch thousands of these independent agents interacting with each other, which will end up with tons of data collected along the way. The most beautiful thing about this is since the agent has memory, we can collect the data by just asking them what happened. For example, here, once the buyer and the seller finish this bargaining process, the system can ask a language model, hey, did you buy the mug? And the buyer will approximately just answer you truthfully, answer the question by saying yes or no, and we can collect the data along the way. So again, in these thousands of independent experiments, we can collect the data from Y1 to probably Y100. After having the induced values for the causes and collect the data from experiments, the language model then can use all various kind of statistical tools to fit the model and validate whether the hypothesis can be verified or falsified. So here's a high-level, previously this is high-level visualization of how the automated system works. And let me share with you some of the results coming out of the real system. So again, the input we give to the system as researchers' input is 2 people bargaining over a mug. And the system builds 3 kind of independent causes, like buyer's budget, seller's minimum acceptable price, and also seller's sentimental attachment, or operationalized as seller's love for the mug. And the outcome, of course, is does a deal occur? There's different treatment levels for each one of the variables. The buyer's budget is actually operationalized as from $3 to $25. Before we dive into the overall statistical model, let's look at the real bargaining process from one of these buyer agent and seller agent. So here, in this plot, the x-axis is a round in bilateral bargaining. The y-axis is the offer in a dollar amount. These two dashed lines are buyer and seller's reservation value, and the rounded dotted line, the dotted plots are basically their offers in a dollar amount. So you can see at the end of the day, a diamond means there's a deal occurred. They gradually approach to a mutually agreed price. We can look at the whole set of experiments. So again, the x-axis is the round, y-axis is offer price. To the top panel, you can see this is the area where buyer have very high valuations and seller have very low acceptable price. So there's a large room for bargaining, and they actually there's a convergence to a deal. If we move down to the bottom corner, there is no room for reaching a deal, so a deal breaks. But at the borderline case where buyer's valuation equals seller's valuation, as I indicated by this square, a deal actually occurs where they should be, just right on this borderline. And we also see that there's a gradual convergence pattern also reported in a previous QJE paper. However, there's some, seems like there's some bad data points coming out. A deal happened where this is inconsistent with individual rationality. But if we go to the transcript, we learn that this is not the case. When a deal is almost close to a dead end, the buyer actually proposed, as in the red line denoted, the buyer proposed do a side deal with the seller. Besides the mug, it also add on something else, and the seller agreed. This kind of works because one possibility is that it may just read the QJE paper and understand the story there's always a gradual convergence between buyer and the seller's price. But alternative possibility that the training corpus is probably just learn a lot bargaining or back and forth seller and buyer bargaining from the internet. Especially there's eBay, there's Reddit. But going back to our hypothesis generated, let's see what does the system actually fit the model. So we have 3 causes and 1 outcome. In simulation, after fitting the data, the answer is $1 increase in buyer's budget actually leads to 3.7% increase in the probability of deal occur. Almost negative effect happens with $1 increase in the seller's minimum acceptable price. And also a unit increase in ordinal scale of seller's love leads to 2.5% decrease. So these numbers, at least the direction of these numbers makes sense. So from this level, the automated system works. But does the system actually, does these numbers, not the direction, but exactly numbers make sense? In order to test this, or the size effect, we actually introduce another validation set of taking the domain of economics, have well-established knowledge auctions. So in this time, we actually give the system this prompt, 3 bidders participating in an auction for a piece of art starting at $50. The system come out, we actually added a little bit, but here's the final model is proposed with buyer 1, buyer 2, buyer 3's budget as the causes, and the outcome is the final clearing price. And the system actually choose an open ascending clock auction as a format so that there's an auctioneer and three bidders to play along. After fitting the model, the coefficients of each pass from buyer X budget to the final clearing price is almost 1/3 on each arm, and each bidder, which means each bidder has almost equal chance, 1/3 of equal chance of being marginal. Let's look at the data in more detail. So here's a subset of the bidding simulation results. The columns are bidder 3's reservation price, and rows are bidder 2's reservation value. The x-axis is bidder 1's reservation value from 100 to 400. And the y-axis is the final clearing price. So we include 3 variables and 1 outcome in this column plot. And each data point stands for a set of experiments where bidder 1, bidder 2, bidder 3 has specific reservation value and 1 specific outcome. According to game theory, this kind of specific format of auctions, open ascending clock auction with private valuation, has its prediction from game theory. So the final clearing price should be the second highest valuation or second highest reservation price. And human experiments also validate this, like this, the data match the theory really well. Why? To give a intuition, if you are the highest bidder and you are sitting in this auction table, once the second highest valuation is hit, you will stop bidding against yourself because there's only 1 people left on the table, and you just accept that price, which is the second highest valuation. So again, these dots are our simulation data. We can plot the actual auction theory, or basically human experiment data on the top of that, and we can see there's a really good fitting. If we zoom out a little bit to the whole set of empirical results, there's also a generally very good fitting between simulation and empiricals. Very good agreement find, but it's maybe just because language model already know the auction theory, or even read the previous human experiment paper. So it isn't that unsurprising. To test this hypothesis, maybe it's the model knows the theory, we directly ask the language model to make a prediction on this auction task. So we prompt the language model, now bidder 1, bidder 2, bidder 3 has specific valuation, and here's the experiment setting. How do you think the final clearing price should be? Well, it's not doing a very good job, and the direct language model predictions are plotted also upon the original data in blue, and you can see the blue lines are flying around. It's not fitting really well, both to the human data and also to the language model simulation data. Actually, we can measure the mean square error for this, and the prediction is almost 70 times larger. So the conclusion is that language model alone cannot predict outcome. We can only simulate the whole game and get a very good agreement data. So the last part of the talk is how do we find something new with this system? So this paper is actually under review, and the review asked us to find something new about humans. This is what we're doing. What are we working on today? Once we get the data, we can try to use the language model system to, iterate the hypothesis. And remember, from our bargaining experiment, we find a really good agreement with the prediction from Nash, and also the gradual convergence pattern from the previous QJE paper. But we also find there's a data point where there's a side deal happened. So in order to do that, which means there's more causes. We have three causes: the buyer's valuation, the seller's valuation, and a seller's sentimental attachment. But this data point means the condition whether a side deal is allowed can also impact the outcome. In order to do that, we asked the language model scientists to come up with more causes. And here we actually have more causes, like the maximum turns of this bilateral bargain, whether cheap talk or natural language is allowed, and more behavioral factors like whether the seller makes the first move or making the first ask, and some partial informations about the buyer knows about the seller or the seller knows about the buyer. Together, these additional 5 parameters and the old 2 parameters renders almost 10K treatments. The beautiful thing about language model simulation is that we can run these 10K treatments, which is impossible for the human experiments. We can run it all in, this is the results for this 10K treatments where each data point stands for one condition. And we actually collect 100K offers and contra offers from language model simulations. And it only costs $150 and 10 minutes to run. This kind of systems can help us optimize the search in this giant design space. For example, which parameters plays an important role, which interaction effects are novel, or can we optimize the whole bargaining process, maybe apply it to the online eBay or Amazon kind of platforms. So here's a very preliminary data on the two-way interaction model I have fitted in, and you already see there are some interesting patterns with cheap talk and also the condition of maximum rounds. The next step we will do for this revision is we will pre-register all the findings from language model simulations with this 10K or even larger treatment space and run human experiments under the exact same condition. So this is the kind of visualization for the human experiment platform we already built, and we are actually running experiments on the top of this, human experiments on the top of this platform. So the last punchline is validation is the bar, and we really hope that the human experiments can allow us to pass the bar. Yeah, so at the end of the day, some future work. I think towards this direction, we will use the new methodology to build better and general proxies, and also apply it to policymaking, market design scenarios in the future. Well, thanks for listening.
So in the interest of time, let's take 1 or 2 quick questions for Kehang.
Hey, a really good talk, Kehang. I just had a question regarding sort of how you were talking about how can we be sure that we're not just having the LLM recreate, a study that it already knows in its training corpus? Have you considered using something like an open source language model where you know sort of what's in its training corpus and what isn't, and then trying to run a study or something that is not in that corpus so you can have some kind of measure of external validity?
Yeah, sure. This is a really good question. Let me iterate this again. Like, how can we run new experiments that never been included in the language model training data before? So in order to actually answer this question, I want to bring up some philosophy paper of, it's actually another MIT Sloan professor, it's Abdullah's paper of running integrative experimentations. The idea is basically we can combine all of these causes that appears in the literature before and run iterative experiments combining all these treatments. So there may be like maybe 20 treatments, 20 treatment causes we can do and combine with 1 million treatments. These 1 million treatments probably never recorded in the human data or like language models training corpus before. So the idea is really to use language model systems to map out as many causes as possible and then run these integrative experimentations with 1 million treatments or even more. And there are definitely some data that was never in language models training data before.
So there's no way to validate that?
Validate?
Yeah, because like
oh, we can run the human data. We can run human experiments. Like
your strategy is just run actual human experiments.
yes.